So I graded your tests, and I, I did not count problem number 7. And if you remember, problem number 7 had to do with um, in it, and I didn't give you. You needed the amount of the inductor. You needed the value of the inductor, not the impedance, because it's a DC problem, not an AC problem. So I couldn't grade it. It was a typo, and I made a mistake. So this problem number 7 is gone. And the average was, believe it or not, between 67 and 80, with everybody but one between 67 and 73. And if you look at my grading, I gave you partial credit on a lot of questions that maybe you shouldn't have gotten partial credit, but I didn't grade off all the way through because it was, anyway, that's the way I grade. Thank me or hate me or whatever. So I'm going to pass these out and wait for a couple more minutes. I wanted to talk to everybody just in general about the philosophy of where we're going, so I want to wait and do that in a minute. So this is the homework, and I graded chapters, I think it's chapter 7. Everybody got it. If you handed in, you got 11 points. I didn't go back and say 11 out of 5. That's what I agreed. So anyway, that's that. Okay, we'll go through this in a minute. I wanted to go through the philosophy of how we got to the point where we're at and why we need to do what we're doing from this point on in this course. So basically, in undergraduate school, when I was an undergraduate, there was no engineering technology where I went to school. There was just engineering, and I'll explain to you the philosophy of how we got to where we got, and then I'll go through with you and tell you how we got and where we got, and why we're getting where we are. So anyway, undergraduate school, typical undergraduate school in electrical engineering, you take circuits 1, well, I did at least, circuits 1, and then circuits 2, and then network analysis. Okay, in that order. And so that's basically what you're doing. You did circuits 1, circuits 2, and network analysis. I did the same thing, but it was done in a different way. This was the sophomore year, supposed to be second semester sophomore. I took it first semester sophomore, but it's supposed to be second semester sophomore, sophomore the second semester, junior first semester, junior second semester. Okay, that's typical of what you're supposed to go through in that order and do that. Now, why you do that is because you need calculus here, and then you need to use all these with calculus. And they explained everything with calculus, but this course here was the AC sinusoidal steady state. But it was all done with slide rules, which took forever. I mean, it was like, that's why I keep going on and on about the calculator, because we spent a whole semester doing nothing but flipping through slide rules. That was all we did. Sine, cosine. We could go back and forth and back and forth and back and forth and back and forth and back and forth, and we learned exceedingly well how to do that. Now, in addition to that, in our junior year, junior first, we had a EMAG course, what we would call engineering electromagnetics. Okay. So when they designed the engineering technology curriculum, they did this as a freshman course with algebra. They did this with algebra, and they waited and waited and waited for you to take this course because you had to use calculus for this course. Okay, so they did this freshman first semester, freshman second semester. You wait through your sophomore year, you wait through your junior year. You're supposed to take this your first semester, second semester, junior year, but most of you wait and take it your second semester, ready to graduate senior year. Okay, because it's the hardest course. You've heard it's the hardest course in the curriculum, and you don't want to take it until you absolutely have to. So the delay here is a killer because you've gone through these first two courses, and then you wait and 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 you wait, and then you take this course. So it's a bit of a harsh reality that you have to do this course. Now, do you have to do this course? And honestly, I think people do make arguments for you don't have to take it. But this course allows you to do the fundamentals course and the PE course, the PE test. And I'll tell you why. When I studied for the PE test, I had been out of school for 6 years. I was scared to death of taking a test, and I didn't know what I would do. But I studied this course, this book, which is the book I had in college. What is this course? What's the title of this book? It's in your course. Yeah. I studied chapter 7 of this book, and I passed. Okay, one chapter done. Okay, so guess what chapter in your book is chapter 7 of this book? Okay, so I'll pass this around. This is not mine. I gave mine away to somebody else, but this is somebody else's. I grabbed after I saw that they. This is the book that I studied, chapter 7, chapter 8, chapter 7, 6, chapter. I'm going to take chapter 7 and I'm going to put it on the web. I'm just going to, copy it, make it a PDF, put it in your you can read through it as well. It probably makes more sense than this chapter that we have. But with this course, with that chapter in that book, you can pass the PE test. That's what I did. And I'm not saying, and also the AC sinusoidal steady states. If you can do that with multiple equations, multiple unknowns. So what you need is you need to know how to do mesh analysis. You don't need to know, nodal analysis is, I put it on your test, but it's like, come on, if you can do mesh, you can pretty well do it, whatever. Mesh analysis, and then mesh analysis, AC sinusoidal steady state, and this chapter 7, you can pass the PE test. So when they were arguing about whether or not to allow engineering technology majors to be able to take the PE test, they said, well, you got to wait 8 years instead of 4 years to take the test. Most people wait a little while anyway. They don't immediately take it, so it's not like you're being punished a lot. But if you want to beat that, you can come back and get a master's degree, and a master's degree is not the hardest thing in the world to get. It's got to be the hardest thing in the world. No, it's not. Once you get your undergraduate degree, master's degree. Okay. Now the other course that you don't get, that I felt like I got hammered on, was this course right here, which is the EMAG course. They teach it here as electromagnetics. So this is the course that has to do with 4 equations like Maxwell's 4 equations. So we talked about that a little bit in the motors course. This is a course in calculus, but basically this is a course in long drawn problems. Okay, so they give you an example, and then you have to decide how you're gonna do it. And then, this was my goal. This is the course that I told you that maybe I don't remember if I told you this story or not, but. So I thought I was pretty good. I got through my sophomore year and I was doing pretty good. I had about a B average. It was about halfway between the two. I wasn't an A student, I was an A B student. Half A, half B, and everything. A third A, 2/3 B, whatever. Got one C, got one D. The D was because, whatever. So I have compassion on people that struggle. I think that's what that was about. But anyway, so I got to my junior year and I was in the throes of thinking I'd made it. I'd crossed the barrier of not making it to making it. And I got into this course and I didn't study that much. I guess I should have studied a little bit harder, but I took the first test and it was 4 tests, 15 weeks course, 4 tests. It's about this one. It's about this one. Every little bit you have a test. And they handed the test back and they put the scores on the board, and the low score was 33. And I thought, who's the poor sap that got 33? And I got 33. And there were people getting 80s and 90s and 70s and 60s and 50s. It wasn't high. There was a smattering of people all the way down to 33. I was the low there. What on earth is going on? I'm not that bad. I'm not that good. I just kind of, I just hurt. And then I studied. I got scared. I studied harder. Second test, I got a 57. I forget it. But then I started looking at what you had to do problems. And what I was missing was there were many steps to these problems, 5, 7 steps to doing problems. Okay. And I was not memorizing or learning the steps. And so what I did was very simple, little 4x6 or 5 cards. I'd write the problem on the front, the answer on the back. And I would go back and I would review these problems and I would work through them. And if I missed a step, I'll look on the back, but if I didn't, I would not look on the back. And I kept doing this. Flip card is what I basically built. And I did that, and I got a 70 something on the third test, and I got a 90 something on the fourth test. And I looked in the end, I think, there's nothing I can do to see in this fourth. Setting, I mean, you gotta be in the fourth. On earth is going on. And the guy told me, I looked at an answer, said, I get a beat in the course, it said, as you were going up, other people were going down. So he said, you gotta be right. He said, you gotta be by honestly points, right in the middle. I didn't give you any special favor in the English special favors. I averaged it by points, you were in the middle, be 5 points. I'm gonna pass this book around because I don't want you to feel bad because you didn't have this course. But on the other hand, this is the course that kind of separates electrical engineers from electrical. This is the one course that does. The course that you got, this one right here, they say, well, you didn't do this or that. Chairman of electrical engineer was very surprised when I told him this is what you did. They do that. Chapter 9. You do chapter 9. So anyway, if you're interested in that kind of stuff, this is the other book. Okay, so those are the 2 books that I remember from college that kind of had an effect on me. So anyway, so why did I ask you about a mesh and a nodal equation problem? I want to make sure you could do them, right? And even though most of you didn't, that was the one I was most disappointed in. I'll crack through this chapter 9 with you. I hate to say it, we'll break it down. It's just like the ENGT 3020, and it's just like EET 4450. So if you've had those 2 or you're taking those 2, you'll see the parallels immediately. It's there, the parallels. So this is the 3rd crack at chapter 9, or maybe it's, if you haven't had ENGT 3020, you should have already, but also EET 4450. This is the heart of that course. This is the Laplace stuff. But you're going to get it with a few more details. Okay. Any questions anybody's got? Any thoughts? So if you are asked ever, what's the difference between engineering and engineering technologists, you'd say, well, he showed us two books. We did the one, we didn't do the other. And that's kind of the truth. That is kind of the truth. But you do things that they don't do, so don't worry about it. That's the long and short of it. And you're very hands-on and they're very good. So what is in this book isn't as important as the fact that it's just these long, meticulous problems. I mean, whatever. Anyway, let's go back. Let's go back and let's look at this problem set and see what we got. Okay, so we're working through the test. These first two, I was kind of disappointed in, and they're not covered as much in chapter 9 as they probably should be, but you probably will run into chapter 9 and this multiple equations more. Honestly, I don't remember if we did, if they were in the on the PE test or not, but I do remember that we had to do this multiple equations, multiple unknowns with AC sinusoidal. We had to do that. I remember that, and I did that. And I don't remember if we had to do multiple equations with chapter 9, the S variables. I just do not remember. But anyway, so you start at some point. I usually say start in the lower left-hand corner, and you start writing, right? It's minus 12. If you walk into it from the minus side, you write minus. If you walk into it from the plus side, you write plus. So you're easy. Minus 12 plus I1 times 2.2k plus, where they fight, you write I1 minus I2, parenthesis, times 2.7k equals 0. Any questions about that? That's one equation. The second equation is, you start in the lower left-hand corner, it is what? I2 minus I1, parenthesis, times 2.7k, plus, and you can lump these together if you want to, and you can say 1k plus 1.5k, or you can just say 2.5k times I2 is equal to 0. Any questions about that? Now, the rest of it is standard form. All right? Standard form is what? It's where you put the I1s, the I2s, and then any questions about that? How do you do that? You sort by I1s times what? I1s times what's with the I1s, what's with the I2s, and away you go. Okay, so it's I1 times what? 4.9k, which is the sum of 2.2 and 2.7, plus I2 times minus 2.7k is equal to 12, all right? I1 times minus 2.7k plus I2 times 5.7k is equal to 0. Now this is ready to be solved. Kramer's rule basically says what? I1 is equal to, You take the 12 and the 0, put it in the determinant. Then you take the minus 2.7k and the 5.7k in the numerator and solve the determinant. It's this times this minus this times this. Okay? It's this minus this over 4.9k minus 2.7k minus 2.7k. Okay, 5.7k. All right, and then you're done. Whatever that is. There's your I1. I didn't ask you to solve it, but that's how you solve it. All right? So that's the determinant method for solving 2 by 2s, and that's, so if you get to a standard form, it's easy to solve. Okay, that's number 1. I just ask you to go to this point and stop. Number 2. Here, you have to physically look at, and I hopefully gave you benefit of the doubt of different paths, but here's your VA and your VB. And this is not an easy one. I didn't give you an easy one. I gave you one that has a little bit of some difficulty to it. This is your VA. This is my VB. This is 1.2K, 1K, 2.0K, 3.0K, and 2.2K, and 8 volts. Now here at A, I said the voltage or the current in is equal to the current out. Okay, so I wrote it around there. So what is the voltage what is the current going in? It's 8 minus VA over 1.2K. Everybody see that? Current in is that. Is equal to the current going out, VA minus VB, over 1K, plus VA over 2K. Current in equals current out. That's at VA. What about VB? You say, well, you drew arrows in a certain way. You can draw them the other way. You can draw them other ways, but you have to satisfy the thing is the current in equal to the current out. So basically, in this case, current in is VA minus VB over 1K is equal to VB over 3K. This is ground, or this is 0 volts, plus VB. Here's just the hard one. VB minus 8 so it's from here, you assume this is minus 8 over 2.2K. If it was below 0, it would be a minus 8, but because it's above, you assume VB is higher than 8. It is not. Okay, this is going to be a negative value. But we just say VB minus, because our current is defined as going this way. It's really going the other way. We see that. But the way I drew it, if I would have drawn it the other way, I would have said VB, this current plus this current equals this current, right? But the way I drew it is VB minus 8 divided by 2.2K, and that's it. I didn't ask you to do any more than that. That was one of the hardest ones, and seemed like, you don't have to do this on any later tests other than it's just, mesh is the one you'll use a lot. In chapter 9, you'll use mesh some, you'll use it, and they'll use it, and they'll also use this a little bit, but basically, this is the other one. This is not the one that's preferred. Why? Dirty, because it's got all these denominators. Okay, that's all that's wrong with that. Okay, now 3, little more difficult, because I asked for 2 things. I asked for the ratio of V out over V source and the current I out over IX. Okay, so what is the voltage over here? It's 15. It's in a negative direction. So the voltage. Okay, what is V out? It's voltage divider. It's 2K over 2.5K, 2K plus 500 times RIX, okay? What is RIX? Or what is R? 15K, right? What is IX? IX is equal to VS divided by 500 ohms. So basically, we can put in there that and we can get our answer, and V out over V source is equal to 15K over 2.5K times 2K over 500, or, and there's a minus sign in front of it, so minus 24, okay? I out over I out is equal to 15K times IX over 2.5K. So I out over IX is equal to minus 6. Probably won't have another one of those. Anyway, that was another question that I think I had given you and I wanted you to be able to do, so that was kind of a try, see how that works. Anyway, here's where I want you to be able to do this, and everybody got number 4, by the way. Everybody got it. Very good. Okay, so it is 10 u of t minus 1 plus 10 u of t minus 4 plus 25, or minus 25 u of t minus 6 plus 10 u of t minus 8 plus 5 u of t minus 10 minus 10 u of t minus 12. Anyway, most of you got it or almost got it. I give you credit for it. If you almost got it, I give you credit for it. That's that one. Everybody got it, pretty much. Number 5. Okay, so what do you do here? Voltage, this is Eli the Iceman. Voltage equals L di over dt. This is a capacitor, I equals C dV over dt. Okay, so this is, I want you to sketch I. Okay. I is equal to C times dV over dt. So C is 0.1 times 10 to the minus 6th. That's C. What's dV over dt? Well, the change is the slope. So it is 20 volts over 2 microseconds. Okay. So it is, what is dV over dt? Is equal to 20 over 2 times 10 to the minus 6th. 10 to the minus 6 cancel out, so I get what? 10 times 0.1, or 1. So I go up from 0 to 1 amp. Okay. And then what happens between, this is from 0, from 1, this is at 1 to 3. What happens at 3? What's dV over dt? 0. So I go back and at 5, then I go up again. This time I go up twice as fast, so it's what? 2. From 5 to 6. And what happens at 6? Goes back to 0. And then it 6, 7, 8. From 8 to 10, it goes down It goes down, but how much does it go down? It goes down 4. Back, and 0. So this is 1 amp, 2 amps, minus 4, 0. Everybody see how the dV over dt plays out? The change dV over dt. It's just straight algebra. Okay. Number 6. Any questions about number 5? Some of you got it. Some of you got it totally right. Some of you got it kind of right. But you got, I mean, it was not a good question, but it was a question that you could pretty much, you should be able to do that. Okay. Number 6. This is the integral one. This is the other brother. This is number 6. This is the integral. Okay, so voltage across it at T equals 0. Current flowing through it is given by this. Okay, so it is, the current is 0, and then 3, and then minus 1, 0. Okay, so it goes up to 3. At T equals 0, it goes up to 3, and then at T equals 2, it goes to minus 1, and then at 4, it goes to 0. So this is 0, okay? So this is the integral one. So I equals C dV over dt. V, take the integral of I, V is equal to 1 over C integral I dt. Okay, so the integral here is what? It's what's under the curve. So that's the summation of the under the curve. So it's at 2, integral of I dt, it is equal to, from 0 to 2, it's equal to what? It's 3 times 2, the area under the curve, divided by what? C. So it's 100 times 10 to the minus 6th. Now, what I should have said was this is in milliamps. I didn't. So this is in amps. This gives me a huge number. What is this number when I get up to there? It's 60,000, right? So it goes up to 60,000. 60,000. It should have been 60. It should have gone to 60. Millivolts, it should have gone to 60, but it didn't. And then you come down, you start at 0. You start at 0, then you climb to 60. If I'd have said milliamps, it would have been 60. And at that point in time, what does it do? It goes to minus 10. So basically at that point in time, it starts going down. So here's 0, here's 2. But then what does it do? It starts going down at half the rate. It was 3, now it is 1, minus 1, but it's going down from 60 to 40. Because you're putting money in the bank, now you're taking it out. So what's the average, what is the overall at this point in time? So you got 6 in and you got 2 out, so you got 40 left. So here is, I'm putting money in the bank here, I'm taking it out. I've got 6 here, I've got 2 here. If I had $6 in, I took $2 out, what do I have left? I have $4 left. 40 is where you're at. And what does it do at that point? It just stays there. This is if you calculate it the way I did, it's 60,000 and then 40,000 volts. That's not practical. It should have said milliamps. But if you did anything like this, I give you credit for it. That's called the integral. That's the integral value. Okay? It's climbing with based on this, the area under the curve, as you go from left to right, it keeps getting bigger. The area under the curve keeps getting bigger, so it grows to there. And that's the integral function. Number 7, I skipped. Did anybody have any questions about number 6? Number 6 is hard. Believe me, this is uncomfortable, but it is what it is, and you need to know how to recognize the integral of a function is what it does. It's a summation, okay? That's what it is. Okay, number 7 we skipped because it's a typo on my part. I'm sorry about that. That should be a value of an inductor because it's a DC problem. Number 8, you come back, and now this is a DC problem, okay? So now we've got a DC problem, and we can solve this. So what do you have to do? Number 8. It's a DC problem with only a resistor and an inductor, okay? So what do you have to do in that case? You have to Theveninize. In order to solve it the way we've done it in the past, you have to Theveninize. So you have to go right here, cut it, and then rebuild it. So basically you rebuild it with R Thevenin, and then you put the capacitor back, or the inductor back on, right? So what would be R Thevenin? 30 volts. How do you know that? Well, it is 330 over 330 plus 220 times 50. Okay, so it's 30. What is R Thevenin? 132 ohms. Okay, now what is I? V over R, 1 minus E, the minus T over tau, where tau is all over R. Okay, what is V? Why is that? The voltage goes up because the current goes to 0, and if current goes to 0, this guy goes to 0, so the voltage goes like this. Okay. If you wrote anything like this with these values, 30 over 132, or V is 30, I gave you credit for it. The I is, this is the current, but then because this is the current that goes down, this is the voltage that goes up. Okay, the current goes down, so the voltage goes down to 0. This is the voltage across V sub L, I sub L, all right? Find the value of V sub L for 50 volts. Well, it's this. Okay. Number 9. Now, number 9 and number 8 are the same thing, although, but they're not, because why? Because now I switch and I ask you for an AC circuit, which has a value of 50. V source is 50 cosine of 500 T. So 2 pi F is equal to 500, all right? Now we have to go back and we have to find what is X sub L, and we play the game with AC. So it's a very different problem, all right? So it comes out to be J100. So X sub L is equal to J100, 2 pi FL. So we've now got a 30 volt AC source and a 132 ohm. That stays the same, but we have over here, we have a J100, okay? All right? What is V sub L? V sub L is equal to voltage divider, J100. See how this works? Where J100 plus 132 times 30, or what? 18.11, angle 52.85. And you're done. See how different these problems are? They're night and day different. I wanted you to see that, and we kind of did that in that one problem we had in the number 9, number 10. Everybody pretty much got this. They cranked through and got this one. Number 10 is just bulldozing your way through. So on the right over there, you have to find this first. What is the resistance over here on the far right? On the far right, it is over here. Let me just start from scratch. All right, so here you start. It's 1.7K, then minus J2, okay. And then you come over here and you've got 3.3K, and then 2.2K, and then J2K. All right, so the goal is to get this part first, and it's 1676.52 at angle 22.29. Then you add that to the others, so Z total equal to 1.7K minus J 2.0K plus 1676.52 at angle 22.29, and I got 3525.8 at angle minus 22.76, something like that. All right, now we go to chapter 9, which says what? We've been talking about special cases. We've been talking about if you did this, if you did that, if you did this, if you did that. Here's the answer. This is the solution if you find yourself in this situation. If you find yourself in exactly the situation, this is how you'd handle it. But what is uncomfortable about that? You got to find the situation, right? You got to find the exact situation. And if you do, then you can use that technique. All right? So now you've been trained to say, okay, pure resistive, easy peasy, resistor in one inductor, Thevenized, resistor in one capacitor, DC, Thevenized. If it's all AC, easy peasy. But what are the real state of affairs across the board? Any combination of and C, any voltage source, how do you handle it? Chapter 9 with Laplace. Okay? So what do you need to know? How many of you have had a Laplace course already? Am I talking to everybody that has had at least one Laplace course? Everybody in here has had at least one, right? Sarah, I don't see it. Have you, yes, 2, 3? Have you had 4450? Have you had ENGT 3020? You're in that now. What about Kang? Have you had a Laplace course yet? No? Not yet. Okay, so we got a challenge here, okay? Because some of you have done this stuff and you kind of know where the bumps in the road are. Some of you haven't, okay? So chapter 9 is kind of a getting you to accept the fact that you can use this trick or this method. It's not a trick, it's a methodology for basically finding any component anywhere using this technique, okay? That's what they say. So basically, what does Laplace do? It takes your differential equations and turns them into algebra, right? That's what it does. And then it turns them back into an answer in time format. So now I can take a DC source, an AC source, any kind of source, and put it to any kind of circuit. And what do I get? I get the real-time answer. It may be a time decaying circuit that goes to zero. It may be a time decaying circuit that does something else. It may be a circuit that goes above. It's not sinusoidal steady state. It is not steady state. What is steady state? That means after you turn it on for a while. It includes steady state, but it is not necessarily just steady state. Does everybody follow that? It's not just well, after a while, this is what it is. This is your answer after it's been on for a while. This is the immediate and the after a while. This is both. So your answers in this, so you're going to come up with answers that are going to be some kind of something e to the minus t sine something plus sine something plus cosine something. You're going to have answers that you're going to have answers with all this stuff in them. Okay? All the above. The answer is, what will your answer be? The answer is all the above. You're going to get the whole thing. You're going to get the whole, do you want the whole thing? Many times you don't really care, but you're going to get it. Okay, so that's what that's what Laplace gives you. It gives you the whole response. The immediate, when you turn the voltage on, and that's why this U of t thing, you turn it on at t equals 0, it does something. Now, we're going to take a few liberties here. They talk about a step signal and then a delayed signal. We're going to ignore the delayed signal. That really, it's there, but we're going to kind of ignore it. So we're just going to talk about a signal that starts at t equals 0 and then it continues at that level from that point on. We're not going to talk about step signals or that type of thing. We're going to, you can do that, and they do, but we're going to kind of say, we're just going to study the ones that are, you turn it on and it's that level from that point on, okay? That's the one concession that I'm making, but it is a concession. Anyway, you can get this far, you can do the rest of it, but I don't think you're going to have to. Okay, so you're never going to have to as far as a test is concerned. You're never going to have to, as far as I'm concerned, you're never going to have to worry about that down the road. So again, I'm not going to try to say this is everything, but it's close to everything that you're going to ever have to do. So basically now, this is a chapter on looking at things in the S domain, all right? The S domain is the frequency domain. Okay? Now, what does S mean? It's got two parts. It's got a real part plus a j omega part. It's got a real part it's got a real part and a wiggle. How's that? So it's got an AC part and a DC part, and it's both. You can have both. S has both DC and AC components in it. So if you say, what is S? What did he say S was? Never be a test question, but it's got a real and a sinusoidal component to it. So if you say it's just a variable, it's like X or T or whatever, but it's just a variable. It's kind of like T, except it has, you can find things based on it. Okay, so it's kind of like anyway, don't worry about it. So also, I teach the 4450 class. Some of you that haven't taken the 4450 class yet will wonder, why do you do it this way? Well, because I can't control when you come in and who's where and what and all that kind of stuff. You've heard all kinds of things about this course, like this is the hardest course ever, what are you going to flunk out with? Okay, I understand. If you persevere, you won't flunk out. How's that? If you walk all the way through and you stay with it, I promise you, as bad as it gets, you won't flunk out. All right. That being said, hang in there. This is the hardest course to get an A in of any in most people's book. They can go all the way through and get all A's, and this course they hit it and it's like, and it's right here. I don't want to scare you, but it's, this is the hard part. Okay, so again, this is the steps to solving a problem using Laplace. And I don't want to get theoretical on you. We talk about this, and you go into the time room, then you go into the frequency room, then you come back again. I talk about that in 4450, and I don't want to bore you. If you've had 4450 with me or whoever, I don't want to bore you. Now, the other side of the coin is, and I think that, and I want to say this, I, I fear that in the past, at some point in time, it's just too hard. We're just going to put all this stuff into microsim and let you solve all your problems. Take it all over to the computer and you can solve it that way, or multi-CAD or multi-math CAD. You can solve these all problems. Yes, you can. That's not the purpose. You can't use MathCAD or MATLAB in a PE test. And one of the only reasons you're doing this is so that you can take that test. There's no, well, I'll put it this way. Only once in my career did I actually use this. And I didn't use it nearly so much as I just said, what the heck is going on? And this chapter showed me what was going on, okay? So, anyway, I was in a factory. Maybe I've told you this story. I don't want to bore you, but I was in a factory, and it was a foundry, and they had they heated brass and bronze. And it was sort of a crude operation, but they had these big panels, and in these panels they had big capacitors, okay? And then out on the floor they had these crucibles they had water going through it was a like a water pipe constructed crucible. So around the crucible there was a wrapping of copper foils like this, all right, and it went back, and this was, so inside this there was they melted the metal. So inside this there was they threw the metal, and then it heated it up magically. I thought at first, and I thought, what on earth are they doing? And all it was they had this circuit like this, and I looked at it as a big old fat old DC circuit, because they had SCRs that basically, they had diodes. It was a diode situation, so they brought a lot of power in, and they made it into a DC circuit like this, and they fed this thing, and it heated this thing up. What on earth? How could this do this? Well, if you look at a circuit like this, and if you take the differential equations, you've got an S squared plus some constant out here. And if you, it basically is like this. The current was, or the voltage is something like this. And this equates to a sine wave, okay, at some frequency. Now, how do you get a high frequency sine wave out of this circuit? How could you possibly get it out of that circuit? If you look at the answers in this chapter, you'll get this. You'll understand exactly why this works. Okay? It's a second order differential equation. And you will see exactly why it solves to a sine wave. Something, sine, something. And it's a high frequency. It's not a 60 hertz frequency. It's a high frequency. Okay? It's how you melt metal. You say, and that's it? That's it. So again, they don't happen that often, but they do happen. And you can walk into a factory and you can say, I don't understand that. I have no idea how that works. And you can live your life that way. You can say, I don't understand it, but it works. Or you can say, chapter 9 out of this book, or chapter 7 out of that book, probably would be able to explain it, because there's no fancies, nothing fancy about it. This was 1960s, 1950s furnaces. This is not space age stuff. This is not some high new stuff. This is old stuff. How did it work? There it is. I felt better. I mean, it's not like I felt like eureka, but I felt like, yeah, that studying that stuff did have some positive impact on my career because I can understand how this works. Not to say that I understand it fully. I don't understand all the little side notes, all the little implications, but I mathematically can take that, look at that, and say, I can see how that happens. That's the only one. I mean, I've worked in industry for a long time, and most of the applications, most of the things that I did not have to do with differential equations. I kid you not. There's very few that do. Now, the stuff with understanding the integral of something or that is important because when you study 4450, you study the PID algorithm, which has to do with the derivative in the integral of a signal, of the error of a controller. And you say, now, okay, so the output of a PID controller is the error, which is the error is equal to the difference of the set point minus the process variable. So you have this controller that turns on an output, which is equal to the error times a proportional value plus the error times the integral of the error times another value. Okay, this would be K1, this would be K2, plus K3, the derivative of the error. So again, that gives you an idea as to how those things work. And that's, I wanted you, problem number 3 and problem number 4 is more about this kind of stuff than anything else. But today, you're jumping into, and this looks strange, and honestly, I can skip over most of this stuff, and I'll just tell you that you don't have to read through this. This part right here is, it's it's not that it's not important, it's just that I'm not going to teach it. Okay? I'm going to go through and tell you that this part of it is not important. Okay? Now, separation of variables is important. And I'm going to show you in a minute that he's talking about here about separation of variables. And that is important. And also this thing right here, Euler's relationship. Honestly, I looked at this when I was an undergraduate, and I looked at that and looked at that and looked at that. I said, how on earth can that possibly be? Okay. The definition of e to the jbt is equal to cosine beta t plus j sine beta t. Okay. Now, how many of you want to accept that and just go on? How many of you think that that's feeding you a line? I looked at that and 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 could never really grasp that equation. Now, maybe you can just see that and say, I got it, that's good. You don't need to know this. This is not something that you need to know, but you're looking at something that is pretty strange, okay? I honestly can get along without a lot of this stuff. Now, what I want you to understand about this is that if you can solve these problems with this, it does explain all the stuff that you've got going on as far as with respect to L's, R's, C's, all different voltage sources. You can use this for every one of them. Okay, so that's that. Now, you can go through this stuff and you can look at it a little bit, and then you say, that's nice, and then proceed on. Now, here is the first thing that you really do need to take note of. Now, I have a better one than this. It's in the other, it's over in the EET 4450 one. And I'm going to give you a copy of this. So basically, you go under hybridplc.org, and then you come down here under courses, You go to 4450. Why is that key? Why is it that I have all this stuff under 4450? Because I haven't taught 3250 in a long time. I taught it from I taught it from 2012. Okay, so this was the course that was passed from. This is the the Holy Grail course. Is what it boils down to. Okay, this is the. Anybody understand what the Holy Grail is? This kind of like the I'm passing along to you the secrets to the kingdom and all that kind of stuff. It's the Holy Grail course. So the Holy Grail course was taught by somebody else because I'm just the old flunky PLC guy. Okay, so I'm teaching PLCs. I'm not the Holy Grail guy. Okay, so the Holy Grail guy was somebody else. And in 2012, the last Holy Grail guy died, and I inherited the Holy Grail. Okay, hard way to explain it, but I inherited it. So from 2012 to 2017, I taught the Holy Grail. We had a book by the name of Stanley. Stanley is not Stanley Steamer, but Stanley was the other guy that had this course. His book was not nearly as. By the way, this book is probably the most famous book the University of Illinois in electrical engineering has. And if you still look on their website, they brag about it. Okay, this book is like, when this book came out, this was the book for all engineering students all across the country to take. And this was taught by Mac Van Valkenburg at the University of Illinois, where I went to school, but I didn't have Mac Van Valkenburg. I had McVeigh. Okay, McVeigh was the guy that I had, but everybody heard about Mac Van Valkenburg. Everybody heard about him. It's like, he was the guy. Okay, now he had taken a sabbatical. He was going back to Utah or something like that. But he wrote this book, and everybody adopted it. And you still look on their website, electrical engineering, they brag about this book. Okay, 50 years later, they brag about this stupid book. It is a good book, and it does have well-written chapter 7. Very well-written chapter 7, because that's, like I said, when I got back into looking at what I needed to do to study for the PE test, I studied chapter 7, went through it again and again and again, reviewed everything in chapter 7 and chapter 8, and I took PE test, got a 90 out of 100 on it, okay? Now, if you really want to know, you take the econ money, so you get 4 problems. I did, and I don't know what you do or not. They probably changed it 10 different times since I took it, but they had 4 problems. The money problem, which is present and future cost of money, is a slam dunk, 25 points. So everybody can get 25% right there. You just one problem, money. Okay, so you take 4 problems in the morning, 4 problems in the afternoon, 1 in the morning, 1 in the afternoon you can take with money. So it's an econ question. Present and future value of money. It's just a formula. It's just a simple formula. Okay, it's 1 over something, and you take it, you write it down, and away you go, and you're done. Slam dunk. As they say, it's a slam dunk. Okay, the other 3 problems that you get are these kind of problems. So you're going to get 3 of this kind, either AC sinusoidal with 3 equations, 3 unknowns, or something like this. You're going to get something like this. So again, but anyway, that's under here. We have the, and I may end up working some of these problems. These problems are better here than they are about anywhere. And I haven't looked at the problems in chapter 9 yet, but here under here is the where is it? Examples under no, yes, under examples. So this got copied again for some unknown reason. Don't know why, but it did. Okay, so under examples is a under examples, Ted. Yeah, I'll put it, yeah, save. Okay, save to desktop. Okay, let's go back. Let's look at it. Under that is a table of Laplace transforms, and I'll bring you one. But if you want a good table, there it is right there. Okay, so this is the This is a better table than the one that they have. Right. So I'm not gonna, I'll bring you copies of it, but there's, if you want a copy of it, there's where it's at. I can't believe that got like that. Anyway. Okay, so I'll get rid of this. Here it is. Maybe it might show up. Maybe not. Well, I want to get out of that. I want to go back and I want to show you what else you need. And this is in chapter 10. So again, they work all this stuff, and I have, like I said, I have not worked all these problems yet, but they do all this stuff. They look at all the stuff we can do. But down here, in chapter 11 or in chapter 10, they actually give you the real keys to the kingdom. Okay. So the keys to the kingdom are in both in chapter 9 and chapter 10, but they give you in chapter 10, they give you a bunch of rules. Okay. So here are the keys. All right. So if I come up to a resistor, and you're going to have to do this, you're going to have to write equations. Okay. So you're now instead of writing in the time domain, you're going to write in the S domain. Okay. And then we're going to convert back to the time domain. Okay. So what is the impedance of a resistor? It's R. Easy. What is the of an inductor? Ah, it's L times S. What is it for a capacitor? 1 over CS. Okay? And they have over here with little caveats with IL of 0 equal to 0. All right? And the current through a resistor is 1 over RV of S. Now this paren S you can forget about, okay? But this part here you can't forget about because so when you're writing these rules down, when you're looking at these rules, 10.8 and 10.9 are golden. And I'm not going to worry about 10.11. What are we going to do? We're going to write our circuits in the S domain. All right, we're going to write in the S domain. And we're going to convert them back to time domain. We'll get our answer, and it's the total answer, okay? So what's the difference between this course and 4450? Ethan, what's the difference between this course and 4450?
You don't know what your additional conditions are in this course?
Right. In 4450, we give you the equations, okay? In EET 4450, we give you the equation you have to evaluate, okay? In this course, you have to write them yourself. Other than that, they're the same course. Once you get to the point where you get to the S equations, the evaluation of the equations is the same. And that's where those of you who haven't had that part of it yet should review. And I'm not going to go back through it a lot. I'll go through it some, but we'll show you basically, and it's really done well in chapter 7 of that book. That's the part that's coming back and writing it is done very, very, very. That's why he is so well known. Because chapter 7, he breaks down, here's a circuit, how do you do it? In the S domain, write it down, and then backfeed it. The initial conditions part of it, you still have to remember, there's some initial conditions that you have to know. So we'll talk about initial conditions as you go through this. But initial conditions are the only part that's left that we have to decipher and how to do that. Other than that, so how do you do this? How do you break this stuff down? You use separation of variables, and you work your way to the point where you can come back to the time domain using things that you know. So some of the time on that sheet, and I'll give you the sheet next time. We won't waste any more time on that today. The sheet is very, very good. But if it's not on the sheet, if you can't find it on the sheet to do the transformation back, you have to then say, how do I get there? And separation of variables is the choice. And there's about 3 or 4 methods that you use separation of variables for, and we'll show you those methods, and then we'll get through that. And that gets you, and it's a review for you if you've had 4450. If you haven't had 4450 or the EET 3020 class yet, or if you haven't had it in the 3020 class, you're going to be seeing it for the first time. It's not hard. There's 3 basic rules, but it's combinations of those rules that get to be difficult. Any questions, any comments? You feeling better or any worse after today? Hopefully a little better. Now you see what's ahead, right? Okay, take care. See you.